So one of the things I want to clarify today is a concept we talked about, but need to stress the importance of them, and that is reference angles. Reference angles allow us to find trig functions for angles that are not between 0 and 90 degrees. You know, when we fall into a rut doing right triangle trig, because in a right triangle, obviously our right angle is 90 degrees, and since the triangle has to add up to 180, each of these other two angles has to be smaller than 90 degrees. So we end up, most of our trig that we do is with angles that are less than 90 degrees, or between 0 and 90 degrees, I should state. Because obviously those can't be less than 0 degrees. But the trig functions do exist for those other angles. So if we go back to our unit circle, put in our reference diameter there, that horizontal diameter, and look at some angles. Let's just take 30-degree angle here. Well, that angle, of course, has a sine, and the sine is the distance from the point where that terminal side hits our circle down to that reference diameter. That length is the sine of 30 degrees. But there are several other angles on here that have a reference angle of 30 degrees. First is what we call coterminal angles. Coterminal angles are angles that have their terminal side on the same spot. Obviously, we have the terminal side here for 30 degrees right there. But we could go all the way around the circle and back there and have the same terminal side. That would be 360 degrees, a full turn, plus the additional 30 to get back to where we're at, 390 degrees. So obviously there's going to be a coterminal side. The angle is going to have the coterminal side in that same spot every 360 degrees. So we have 390 degrees. We could add another 360 degrees to get 750 degrees. That would be the same terminal side. And we could keep going. We could keep adding 360 degrees. All of them are going to have that same sine because their terminal side is in exactly the same place. Other ways to come up with angles with the same sine is to look in other quadrants. Now, it's traditional to put in the second reference diameter here, that complementary reference diameter going vertical there. Let's put back in our 30-degree angle here. And of course, this is our sine. There are four other places, four other locations for a terminal side on this circle where we have that exact same length of sine. If I go over here, this of course was the first quadrant. If I go over here into the second quadrant, that's the angles between 90 and 180 degrees. There's a spot right here that has the exact same sine. That length is exactly the same. The terminal side of that angle would be right here. And what we know about that angle is that its reference angle has to still be 30 degrees. So we can find that angle, it's going to be this angle, by using what we know about our geometry of angles. And we know that this straight line is 180 degrees. If we subtract that 30-degree reference angle, this has to be 180 minus 30, or 150 degrees. So at 150 degrees, because it has the same 30-degree reference angle, we have the same sign as we did at 30 degrees. Now, if we keep going into the fourth, or the third and fourth quadrant, we can have a 30-degree reference angle here, and we can have a 30-degree reference angle here. Both of those will have signs that are still that same length. Now the difference here is if I can compare that to my sign for a regular 30 degrees, this sign here, of course, is positive. It's above that reference axis. Down here, these signs are negative. They're below the reference axis. Let's find the angles associated, the absolute angles associated with each of those reference angles. So for this first one here, this is the angle associated with it. Well, that's 180 degrees to here, plus the 30 degrees, makes that a 210 degree absolute angle. Over here, this one would wrap around like that. It's almost a full turn. In fact, it's 30 degrees short of a full turn. That'd be 360 minus 30. That's going to be 330 degrees for that absolute angle, for that reference angle there. And if I turn on my calculator, and I'm going to remember to set the mode before I do my first calculation. So the sine of 30 degrees, that was our original angle here, is 0.5. Now we also had that 30-degree reference angle over here. And remember that 30-degree reference angle was associated with 150 degrees there. If I do the sine of 150 degrees, it's also 0.5. For my other angles that have the same 30-degree reference angle, if I do the sine of 210, it will not be 0.5, it'll be negative 0.5. And of course over here, the sine of 330 is also a negative 0.5. So the 210 and the 330 are not the same sign, but they're a related sign. They're just the opposite direction. And those coterminal angles, like we said, this could be 390 degrees. Sine of 390 degrees is also 0.5. Or this one could be 150 plus 360, and that could be 510 degrees, sorry. Sine of 510 degrees is still 0.5. So all of those angles will have a sign that is the same. They're 0.5 or negative 0.5 because all of them have that same reference angle. That is the importance of those reference angles in the work that we're doing. Now, we're still going to be relating our trigonometry for now back to a triangle. But there are applications that go outside of that. We're going to be starting oblique triangles. And really, oblique is just a fancy term for a triangle that has nothing special about it. In other words, there's no right angles in that triangle. This is an oblique triangle. If I call it triangle A, B, C, of course we'll have sides little a, little b, and little c. We label the sides by the angle that they're across from again. There's obviously no right angle in this, so it's not a right triangle. But we do have angle C here, which is an obtuse angle. Because it's still in a triangle, there are limits to the size of those angles. Because the angle sum of a triangle is 180 degrees, and obviously no angle can be negative, each angle to be between 0 and 180 degrees. You know, we could have one that's 79.9 degrees, but then the other ones have to be like 0.05 degrees each. They have to be really, really small. But it is possible to have an angle that's not quite 180, but right up to it, really close to 180 degrees. Because of that, we need to be able to do trig functions in both the first and second quadrant of our unit circle for triangles. We're going to come back to that in just a minute. There are other applications of trig functions. Well, if we were looking at this unit circle, now this next little part, by the way, not going to be on a test or quiz. I'm just showing it to you so you can see where it would be used. But let's look at the value of sine theta as theta goes around the unit circle. I'm going to make a graph here. This is going to be my angle. This is going to be the sine of my angle. This will be positive 1. This will be negative 1. I'll label this 90 degrees, 180 degrees, 270 degrees, 360 degrees. So at 0 degrees here, the sine, which is this height, is 0. If that angle is 0 degrees, the reference angle is 0 degrees, that terminal side lays right on top of our reference axis. There is no height up to that point. As that angle increases, the size of the sine increases until we get up to 90 degrees. At 90 degrees, that sine is 1 unit. But 90, it's 1 unit. So when the side is moving here, it increases rapidly until it gets up here. The length of that sine increases very slowly. So it's not a straight line. It's a curve, something like this. Or like that. There we go. Now, as it continues, as the reference angle, or the terminal side, I should say, continues past 90 degrees, the sine gets smaller. Again, it gets smaller slowly here at first, but over in here, it starts to get smaller very, very quickly until it hits 180. At 180 degrees, again, that sine is 0. Again, it gets smaller slowly at first, and then quicker towards the end. And then, of course, this does the similar thing down below in the negative side of our reference axis. The sine gets more negative until at 270 degrees, the sine is negative 1. And as we go back the other way, at 360, we get back to 0. And this would continue as we went for terminal side, the terminal side would still stay within that circle, but as our angle went from 360 to 450 to 540 and kept going, that cycle would keep going. This is called a sine wave. And that sine wave is very important in a lot of applications. Millwrights deal with this a lot because setting up the electrical for heavy equipment, you're dealing with all of your electrical power. What comes out of the outlet on your wall is in a sine wave. It's alternating current. Now, it's not +1 to -1 like the pure sine wave. It's actually, for a 110 volt outlet, it's from a positive 170 volts to a negative 170 volts. The voltage follows that cyclical wave, and that's what allows the motor to turn. It goes from positive as the motor makes its first half turn, then it goes to negative as it makes the second half turn to reverse polarity to keep it running. You hear about 1-phase, 2-phase, and 3-phase power. Single phase deals off of a single sine wave, again, 170 to a negative 170 volts. The average voltage that comes out is 110 volts away from zero. That's why it's called a 110 or a 120 outlet. Is the average is actually it's like 111 point something. Is the average voltage, or the average distance from 0 volts is the way it really is described. But to get a 220 outlet, they call it a double pole breaker. Actually, I'll just do it right here. There's a second sine wave, a second current source that, wow, that's horrible at the end there, but you guys get the picture. It's also in that same service. There's actually 2 sine waves always coming in. For a 110 volt outlet, they tap into the sine wave and then ground it back to the ground. For a 220 volt outlet, they connect to one sine wave and the other sine wave, and you notice that literally doubles the distance, or doubles the available voltage. That's how it goes from 110 to 220. So the sine wave going beyond 360 degrees is very important. It actually goes on for infinity. It goes on forever. It's used for that. It also is used for rotational motion. If I'm looking at a shaft that is spinning, and let's just say there's a keyway on the shaft, and if I want to look at the location of that keyway above the center of the shaft, well, at 0 degrees here, it is at the same height as the center of the shaft, so it's at 0. At 90 degrees, it's whatever the radius of the shaft is. At 180, it's 0 again, and it keeps going up and down. It'll follow that sine wave going up and down, even with the shaft, above the shaft, below the shaft, and round and round. So angles bigger than 360 degrees, or bigger than 180 degrees even, are important in other applications. Being able to find the trig functions of those angles is important in other applications. With that said, those are not applications we're going to get into in this course. For what we're going to do, we're going to stick to triangles, because this is not an electronics-based course. It is a geometry-based course. And when you're dealing with geometry, the triangle is really where your trig applies. All of our angles will be between 0 and 180 degrees. But now with that said, if I have a triangle like this, A, B, and C, not a right triangle, but our trigonometry still applies to an oblique triangle. And if we calculate here and we find that the sine of angle C has to be 0.382. To find angle C, we would do an inverse sine of 0.382. That gives us 22.46 degrees. Well, obviously, that is not 22.46 degrees. It's an obtuse angle. So since C is obtuse, we know two things. One, we know that C is between 90 and 180 degrees. And because it's between 90 and 180 degrees, that means it's in this second quadrant of our unit circle. We know that the reference angle for C is 22.46 degrees, but not C itself. So how do we find C? Well, if you recall from that unit circle, if this reference angle is 22.46 degrees, angle C is this angle, it is the complement, or not the complement, the complement would be 90 degrees, this is from 180, it's the supplement. Of 22.46 degrees. So it's 180 degrees minus 22.46 degrees, giving us 157.54 degrees. We will talk a lot more about this on Monday. Monday, Tuesday, and Wednesday next week, we are going to be working with these oblique triangles. I'm going to give you a little bit of an easy set of homework for today. We're going to finish off the packet that you guys got before spring break. It's page 374 in that packet. Just a single page of trig functions for angles that are not our standard between 0 and 90 degrees. So work on those. Make sure you remember how to calculate those. Next week, like I said, Monday, Tuesday, and Wednesday, we're going to work on these oblique triangles. How do we apply trig to those oblique triangles? It comes down to law of sines and law of cosines. Now, I get asked it all the time, well, there's a law of sines and there's a law of cosines. Is there a law of tangents? There actually is a law of tangents. If we get some free time, I'll show it to you. Probably not next week. It'll probably be after Easter before I come back to it. Law of tangents is not nearly as useful as law of sines and cosines because it kind of involves creating a system of equations. Actually, it's a way to avoid doing a system of equations, but we'll take a peek at that after we're done with this unit. So anyway, I'll turn you loose to work on that. And we'll see you all. You guys have a great weekend. We'll see you all on Monday.